Section 5.3 Diagonalization. Some applications of linear algebra involve computing powers of a matrix. For example, multiplying by A may represent the transformation of certain data over a given time interval. Multiplying by A squared represents two intervals, etc. Using eigenvalues and eigenvectors, we can change some matrices into a form by which powers are easy to compute. So let's look at a definition. A square matrix A is diagonalizable if A is similar to a diagonal matrix. That is, if A is equal to P times D times P inverse for some invertible matrix P and some diagonal matrix D. And remember, we looked at the definition for being similar in the last section. So now powers of a diagonal matrix are easy to compute. For example, if we're given this matrix D, it's a diagonal matrix. I have numbers on the diagonal and zeros everywhere else. Then D squared would be basically multiplying my matrix D by itself. So I'm going to write two matrix D's down. And remember, when we multiply, we go across each row and down each column. So when I multiply, then I will end up with 2 squared, 0, 0, and 3 squared. And this forms a pattern. So we see then that d to the k power is going to be equal to 2 to the k, 0, 0, 3 to the k, and this is for k greater than or equal to 1. And remember, this is for this specific matrix D that we were given. If A is diagonalizable, then we know that A squared is equal to PD P inverse times PD P inverse, since we know that if A is diagonalizable from the definition on the previous slide, that A is equal to PD P inverse. So A squared is just simply that multiplied by itself. So if we follow that out, I'm just going to change the grouping. So I've grouped P and D together, and then D and P inverse, and then I've grouped P inverse P. And so what we see then is that P inverse P is equal to the identity matrix. And whenever we multiply by the identity, we know that it basically disappears. It's like multiplying by 1. So then we're left with P times D and then D times P inverse. So reordering again, we see that D squared is what we end up with here in the middle. And so then we see that A squared is also diagonalizable. And so in general, A to the K is going to be P D to the K P inverse. So we have a question then. When is A diagonalizable if we're given a matrix A? To answer that, we have a theorem, Theorem 5. An n by n square matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So the dimension of the matrix is how many linearly independent eigenvectors we need to have. Furthermore, for A equal PD P inverse, then the columns of our matrix P are the n linearly independent eigenvectors, and the diagonal entries of our matrix D are the corresponding eigenvalues in the same order. That is, A is diagonalizable if and only if there are enough eigenvectors to form a basis for Rn, and this happens to be an eigenvector basis. So let's look at an example. We want to diagonalize this 3 by 3 matrix A, and we're going to follow it step by step. So we're going to find an invertible matrix P and a diagonal matrix D such that A is equal to P D P inverse. And remember what we just saw from Theorem 5 is that our matrix P is made up of our eigenvectors, and our matrix D is made up of the eigenvalues on the diagonal. So step 1, we need to find the eigenvalues of A. These will usually be given to us when the matrix is larger than a 2 by 2. We learned how to find those for a 2 by 2 matrix. However, there's a lot more calculation involved for a larger matrix, so we'll typically be given those. So in this case, the eigenvalues are lambda equal 1 and lambda equal -2. Now for step 2, we need to find 3 linearly independent eigenvectors of A. If there aren't 3 linearly independent eigenvectors, then A is not diagonalizable. So the method of section 5.1 produces a basis for each eigenspace. So remember, we're going to look at lambda equal 1, and we see that we're going to look at A minus lambda I, 0, and we're going to row reduce that matrix. So we're going to first find A minus lambda I, and so we'll have this matrix here, and then we'll include our row of zeros, and we will row reduce. So we get this matrix here, and we see that we will have x1 equal to x3, x2 equal to negative x3, and x3 is free. So then what we've got is x3 times 1, -1, 1. And so then this vector here is going to be one of our eigenvectors. And now let's look at lambda equal -2. We're going to again set up A minus lambda I and then 0 in our augmented matrix. And we'll have this matrix here, which we want to row reduce to get this matrix here. And so we see that we have x1 is equal to negative x2 minus x3. x2 is free, and then x3 is also free. So we're going to have 2 eigenvectors here. We have x2 times -1, 1, 0, plus then x3 times -1, 0, 1. So then now these 2 vectors are going to be our other 2 eigenvectors. And it's easy to check then that those 3 vectors are a linearly independent set. So step 3 is to construct P from the eigenvectors. And so you'll notice down here at the bottom that I've listed those, and we've called them B1, B2, and B3. Those were the eigenvectors that we just found. So our matrix P is going to be made up of those 3 eigenvectors. So we simply list those. The first one is column 1, and the second 2 are column 2 and 3. Step 4 is to construct D from the corresponding eigenvalues. So we're looking at our lambda, and remember they need to be in the same order, so you'll notice that lambda equal 1 goes in our first pivot position on the diagonal. Lambda equal -2 then goes in the second and third positions on the diagonal. To check that P and D really work, we can verify that AP equals PD. And so really you can either check this, which is a simpler form, or you can check this equation up here. Using a calculator, either one is easier. However, if you were doing it by hand, this one would have been easier to check. It wouldn't have required you to find the inverse of P first. So now let's diagonalize this matrix. Step 1, remember, is to find the eigenvalues of A. Now typically those are given to us. However, this matrix is not going to be that hard to find them. So to find them, we want to find the determinant of A minus lambda I. which is going to be the determinant of this matrix here. So notice that we have a row with zeros in just one term, so the determinant is rather easy to do. So we'll start out with just 2 minus lambda, then times the determinant of the matrix that's left when we eliminate that row and column, which is 2 minus lambda, 1, 0, and 1 minus lambda. And so then that is going to be 2 minus lambda times 2 minus lambda times 1 minus lambda, and then minus 0. So this is what we end up with. And you could rewrite this as 2 minus lambda squared times 1 minus lambda. And to find the eigenvalues, we need to set that equal to 0 and solve that equation. So if we set that equal to 0 and set each of our factors equal to 0, we'll end up with lambda equaling 1 and lambda equaling 2. So these are the two eigenvalues that we have for this matrix. So now I want you to try the rest of this problem. We found the eigenvalues in step 1, so I want you to finish steps 2 through 5. Step 2, you need to find 3 linearly independent eigenvectors of A. So remember that you're going to be solving our equation A minus lambda I times our vector x equals 0. So you're setting up your augmented matrix for A minus lambda I and 0 for each of our eigenvalues, and row reducing it and finding the general solution to get your eigenvectors. Step 3, construct P from the vectors that you found in step 2. Step 4, construct D from the corresponding eigenvalues. And step 5, check your work by verifying that AP is equal to PD. So make sure you're able to work on this, and we'll discuss it in class. Now we're going to look at another example where we want to diagonalize this matrix, and we're going to see something happening a little different in this one. So step 1, we're going to find the eigenvalues of A, and in this case we're told that lambda is equal to 2 and lambda is equal to 4. Now when we look at the next step where we want to find the eigenvectors corresponding to those eigenvalues we were given, we see that a basis for lambda equal 2 is one vector, where we have v1 equal to 1, 0, 0. And a basis for lambda equal 4 is v2 equal to 5, 1, 1. Now you should notice that we kind of have a double root with lambda equal 2, and we should have ended up with 2 vectors here, but we didn't. So what we're seeing then is that every eigenvector then of our matrix A is going to be a multiple of those 2. Which means there are not 3 linearly independent eigenvectors of A. So then by theorem 5, A is not diagonalizable. So it's very important that we make sure that we end up with the same number of eigenvectors as the dimension of our square matrix. So now I want you to diagonalize this matrix A, it's a 4 by 4, if possible. Remember that first you need to find the eigenvalues, then find the eigenvectors, and then set up your matrix P and your matrix D. But check before you do that to make sure that you end up with 4 linearly independent eigenvectors. If not, then it's not possible to diagonalize this. So work on it and we'll discuss it in class. In this example, we want to answer the question, why is this matrix A that's a 3 by 3 diagonalizable? We know that the eigenvalues are going to be lambda equal 2, lambda equal 6, and lambda equal 1. So our matrix A has 3 distinct eigenvalues. So since eigenvectors corresponding to distinct eigenvalues are linearly independent, A then has 3 linearly independent eigenvectors, which is how many it needed to have. Therefore, A is diagonalizable. So that leads us to Theorem 6, which says that an n by n square matrix with n distinct eigenvalues is diagonalizable. So if you have a 3 by 3, you have 3 eigenvalues that are distinct, then we know that our matrix is diagonalizable without having to do any work. And our last theorem is Theorem 7. We want to let A be an n by n matrix whose distinct eigenvalues are lambda 1 through lambda p. So there's 3 parts to this theorem. The first part, part A, for our values of k between 1 and p inclusive, the dimension of the eigenspace for lambda sub k is less than or equal to the multiplicity of the eigenvalue lambda sub k. So basically what that means is what we saw before. If lambda has a multiplicity of 2, then when we solve our equation, our characteristic equation, and find the eigenvectors, we are going to have 2 or less. Part B, the matrix A is diagonalizable if and only if the sum of the dimensions of the distinct eigenspaces equals n. And this happens if and only if the dimension of the eigenspace for each lambda sub k equals the multiplicity of lambda sub k. So we saw before in our example where the matrix was not diagonalizable that we had a lambda eigenvalue that had a multiplicity of 2, but the eigenspace had only one vector in it, so it had a dimension of 1. And so when you added the 2 together, you only had 2, and what we needed was 3 in that case. That was just an example to prove this theorem. So in order for A to have been diagonalizable, that eigenvalue needed to have had 2 eigenvectors corresponding to it, since it was a multiplicity of 2. And then part C, if A is diagonalizable and beta sub k is a basis for the eigenspace corresponding to lambda sub k for each k, then the total collection of vectors in the sets beta sub 1 through beta sub p forms an eigenvector basis for Rn.